In this video, we're going to investigate the plausibility of space elevators using a ninja physics approach. So the idea is to get things into space by going up an elevator rather than large amounts of rocket fuel and other such wasteful things. So we're clearly going to need to have an elevator going up to space. We're going to need some sort of structure that can be attached to. There are two obvious possibilities. One is we have the Earth here, and we have a really big building. And we just go up the building. It might need to be a pyramid-shaped building to give it enough strength, or a tall tower or something, but it doesn't really matter. The second possibility is that we know there are objects that just float above the Earth. There are satellites in orbit. Maybe we can just drop a rope down from one of them to the Earth's surface. So let's look at these two possibilities in turn. The tall tower, the atmosphere is about 50 kilometers thick, so it would have to be more than 50 kilometers thick. That's a lot bigger than any tower at the moment, but perhaps not impossible. The problem with this is, first of all, that it's all supported at the bottom, so that it's quite likely to bend the Earth's crust underneath it, and the whole building is in compression, and materials are not very strong in compression, they tend to crush. Whereas this structure here is in tension, it's been pulled down from above. That means it's not putting any stress on the Earth's crust, and materials are much stronger in tension. This tower concept as well, the trouble is if you are at the top and you launch a space probe, it'll immediately fall straight back down again. The reason being the tower up here, maybe 1,000 kilometers high, is not going at anything like orbital velocity. So what you would need is a big catapult at the top, so the spacecraft would come up here and then be fired sideways at orbital speed of about 20 kilometers a second, which is a possibility. The drawback of this, well, unless the satellite goes around once every 24 hours over the equator, then the bottom is going to be dragging around the Earth. So for example, if the spacecraft that you drop the cable down is in a low Earth orbit, that goes around every 90 minutes, and so the bottom is going to be travelling at hypersonic speeds around the Earth doing enormous damage. It's not very convenient. So it makes a lot more sense to have the spacecraft up so high that it's in a geostationary orbit, which means 36,000 kilometers up, which is a long way, which is a drawback. But then it will appear to sit over one point on the equator, and you could indeed have a proper tethered rope attached at both ends. The weight of the rope will pull the spacecraft down a bit, so you might need to have a counterweight going out the other side to balance that. Okay, so that's the idea. Which makes more sense? Well, they both could work. In this case, you could in principle build a mountain, artificial mountain, maybe 30 kilometers high, so it's above the most of the Earth's atmosphere, and then have a big railgun catapult or something on top that would fire the things out at 20 kilometers a second. You can't do that on the Earth's surface because it would burn up. But if you can get above most of the atmosphere, you might be able to do that. So that's actually quite feasible. We could investigate a catapult system like this. But for the moment, let's investigate this idea that we have a spacecraft at geostationary orbit and a cable going down. What's going to be the limiting factor here? Well, the thing that worries me is how strong the cable is going to be. So let's zoom in on the cable. So we've got the cable. Let's take any given slice of the cable. It's going to have gravity pulling it downward. And if we work in a rotating frame of reference, it's going to have a centrifugal force outwards. There's going to be a tension downwards and a tension upwards, which will not necessarily be the same. The tension may change as you go along the cable. And then you've got your lift buggies maybe going up tracks on the side or in the middle or something like that. But they're going to be negligible in mass compared to the actual cable itself. So if you consider some bit of the lift quite low down, mg is going to be much more than mv squared over r, because the gravity is going to be very strong. G is being in the inverse square law, and the centrifugal force is going to be quite small because it's not going that fast. As you go further and further out, the velocity gets larger, so the centrifugal force gets bigger, and also the gravity gets weaker. So most of the tension is going to be pulling the bottom bit. So let's look at, say, the bottom 1,000 kilometers. How much tension is needed to hold that up? Well, let's assume there's some cross-sectional area for the cable A, so the volume is going to be a times the length, which is 1,000 kilometers. And we'll give it, let's say it's made out of something like Kevlar or some extremely strong plastic. They have a density about that of water. So the mass is going to be approximately A times L times the density. Multiplied by G. For the bottom 1,000 kilometers, G is not going to be very different from the surface of the Earth. It's going to be about 10. So what's that come out as? So let's assume we've got 1 square meter. So that's 1 times the length of 1,000 kilometers. So that's 10 to the 6 meters. Density is 10 to the 3. G is 1. That's 10, sorry. So 6. So it's about 10 to the 10 newtons for a 1 square meter cable. Now the strongest materials known are things like Kevlar, which have a maximum breaking pressure of about 5,000 megapascals, which means if you have 1 square meter of them, they can supply maximum tension of 5,000, which is 5 by 10 to the 9 newtons. So that's not too far off. If they were maybe just twice as strong, these strong materials could actually maybe match this. That's only for the bottom 1,000 kilometers, of course. You're going to have the next 1,000 kilometers and the next and the next. Each next 1,000 kilometers you add is not going to be as bad because the gravity is getting weaker and the tension is going to get stronger, but it's clear that it's going to increase things, so the actual tension you're going to need is going to be a few times that. So maybe we're about a factor of 10 out. Not too far, we're almost within shouting distance, but not quite there. So basically this cable is not strong enough to hold itself up. You can think of it a bit like having a crane and dropping a cable from it. How long can the cable be before it snaps under its own weight? Only in this case it's a bit more complicated because there's some centrifugal force and weaker gravity at the top end. But it looks like we're about a factor of 10 out. So if you could have material that was 10 times stronger, you could actually build a space elevator. Carbon nanotubes might do that. An alternative idea that's been proposed is actually what's called skyhooks. The idea is that we have the Earth, and instead of trying to go all the way out to geostationary orbit, we have our satellite in quite a low Earth orbit with a whole bunch of wires extending from it that are almost as long as touching the way down to the Earth. And what we do is actually have these wires rotating very fast this way, so as the spacecraft goes around the Earth, the bottom wire is almost stationary with regard to the Earth's surface. So what you'd see on Earth is a wire would sort of come down, reach its bottom point, and then go back up again. And in principle you could fly an aeroplane underneath and hook cargo onto it and it would then be carried up into space. So this is a skyhook idea, and because the cables only need to be a few hundred kilometers long, we could probably build them with modern technology, not requiring something future like carbon nanotubes. So also this railgun approach might work. So there's 3 possible approaches here to getting things into space much more cheaply than we can currently do it.